Yeah.
Um,
No, I will just briefly go through it. What I was saying earlier.
sure.
So,
Okay, I'm just gonna stop the camera and mute. Go on mute.
okay. So
It's all
let me.
good now.
Okay. Good. So let me go here and then hide. Okay, do all the stuff. You have to do it every time. Uh, we are still live, right? It's okay. Stop subtitle. Okay. So I can continue and we are live. Okay. So sorry, Fox, that I was muted. I didn't realize that I wanted to finish fast. So started, and thanks for Christopher reminding me. And then I will just briefly go through this. And I was mentioning uh, essentially, uh, that this episode is very important because the eighth episode we have to cover belt theory because that's a very important aspect of quantum computing. So we have to do one more episode, so to say, the skip to the next episode, which is this one, to get to the M theory that we discussed with Christopher as well. But then, as we mentioned briefly, that European conference will be in May 28th to June 2nd, tentatively. Again, we are working out the details, Christopher, and we'll update that as things go on. Hopefully, by the end of the month, we'll have a complete understanding of, like in Budapest in Hungary, how we are going to do that. So that's the aspect. And after the ninth, there'll be the 10th episode where we one of the final ones, emergent theory. So we are already in the contemporary history because even the M theory is part of our generation. Uh, then we go into the documentary movie, things like that. So we'll keep updating about that. You can also watch live at this YouTube TechNet platform as we speak and also previous episodes. So that will help you. And then we have the World University eventually, hopefully establishing by the meeting, European meeting in the May. Uh, so those are going on. So let me briefly go through it again. You may have seen this video without my audio, but essentially I started the historical perspective, a theory in quantum gravity, and in theory essentially tried to unify the five string theories that came up. The quantum gravity, try to merge quantum mechanics, general relativity, and M theory is a very important part of that. And you have these references. Okay. So the roots of M theory is based on starts from Newton gravity, which started from Galileo's original experiment after droppings of objects from Leaning Tower of Pisa, and we know that we covered in the previous episodes. And gravitation force was important, and then but Einstein said the gravity is a secondary effect because of the curvature of space-time introduces gravity. So that changed. Quantum mechanics again started the behaviors of particles. That's why I mentioned the previous episodes. We had the scientists experimentally found particles like electron, proton, neutron, things like that, and that changed the structure of the atom. That there is something more inside. But all of these theories became more mathematical, as we mentioned before. But the string theory again became the abstract math, and it's a beautiful math, but there are no observables. And then eventually developed into five distinct versions. They're trying to see are there any observables possible, things like that. Again, these are the references that you can look into the more physics aspects of this. The birth of web theory, again, 1995 is really when it started because there was a confusion about the five distinct string theories. And Edward Witten was one of the persons in 1995 tried to unify at the umbrella of M theory. Uh, and then he said all of them are part of a single theory and it's highly mathematically abstruse. Uh, but it proposes 11 dimensions, 10 spatial, and then one time dimension. And the key features in theory is that brains again replaces the idea of strings. So again, it's more like a two-dimensional. You can kind of think briefly because I used to work in physical electrochemistry that it's like a thin film kind of thing, but it's much more complex, mathematically complex thing. So the brain is supposedly three-dimensional, which is tried to simulate the Euclidean thing that we see normally, Euclidean geometry, but in a higher dimensions space. I will try to show some pictures in two-dimensional aspects that give some idea of that piece, but you have get more understanding uh, from the actual physics that I am putting the references here. So dualities in M theory, different string theory equivalent to discrete same physical reality. Like I work with the Emery Taylor of Discordium. We talk about many different realities, and that is a separate topic by itself. But in any case, we have some presentations in a separate way there all as well. So supersymmetry relates fermions, which are the actual matter particles, the matter or the particles, the real particles that we interact with, that we see actually originally are fermions. But the bosons are the force carriers. Bosons, for example, the light or photon aspects, they're the force carriers. Again, we went to some details before. The theory says it is that there are super partners. Again, it's very hard to see in place like LHC experimental measurements because it needs very high energy that we are not able to achieve yet. I don't know about future whether we'll be able to achieve that or not, but that's something we have to get tuned to. Again, these are the references and the quantum gravity and theory. So there is a try to unify the general relativity and quantum mechanics, which doesn't right now. There's a lot of inconsistencies, especially with the vacuum catastrophe, things like that. There are a lot of problems merging them together. So, in theory, try to describe gravity in a quantum mechanical framework and try to explain black holes, singularities, and cosmology. This is very important because black holes are the result of the general relativity, Schwarzschild metrics, and things like that. Singularities, again, is the fundamental thing, again, that points to the how the universe is produced. Uh, in terms of inflation theory, things like that. There are a lot of conflicts and contrasts, and people are debating back and forth about these. Cosmology is very important, and I recognize the field right now. I would call it quantum cosmology, which would be one of my main areas after I introduce the new ongoing publications, especially the abstract to real, the what you call the particle physics. Uh, that just using spin spectroscopy, you can do E over M versus spin, which are available data. And when you plot that, you can see whether the gravitons exist or not, and you can have the experimental design to find the gravitons are really exist, or we can ever observe that. This is one of the things we want to uh, evaluate whether it's ever possible to observe meaningfully observe graviton. So M theory predicts existence of gravitons, quantum particles that mediate the force of gravity. So gravitons are the quantum particle, very important connection that we need to understand about in quantum gravity. Again, these are the Rovelli and Bruman. They are the some of the top level scientists who are examining that in more details. Uh, okay, so string theory and black holes. So black hole information paradox, as we know from Hawking and other people, uh, the quantum mechanics suggests information is preserved, but relativity says that it's lost within the black hole. So there is this thing going on that we have to resolve these aspects. And then again, uh, the holographic principle is again upcoming thing. It's for all information. The volume of space can be encoded on its boundary, so we can obtain the information on the boundary. Hence, uh, you know, that idea gets linked to M theory, and the idea of quantum gravity comes from that. Again, Maldacena and Bernados et al. They have gone into details about these. M theory and the early universe. So cosmic origin. M theory may elucidate origins of the universe. Big Bang scenario where multiple brains collided, creating. So the Big Bang scenario, they are trying to preserve that, and many scientists, including us, questioned whether there was ever a Big Bang or universe was produced in totally different manner geometrically. But the brains colliding would be a scenario that could suggest a Big Bang. String gas cosmology. It proposes string gas cosmology, alternative traditional inflation. So again, like singularity inflation, there are problems there. The dynamic strings may explain cosmic inflation and universe explain. Again, trying to preserve those aspects of the uh, inflation and other things. So these are discussed more about the cyclic model with the Steinhardt and cosmic effects with the Alexander et al. They are discussing more the physics and the mathematics. Okay, so we'll just go through some diagrams here so that we get an understanding. The M2 brain. So M theory, extension string theory, as we it's not point particles. We know that diagram, which visualize as a wavy lines representing that. So a brain diagram is one of the things I'm showing here. The higher dimensional brains, these are like brains that can have different numbers or dimensions. So briefly, it will look like that 2D surface in a 3D space. Uh, so trying to plot that. So so 2D will be a surface and the 3D will be a volume type of thing. So that's plotted there. And here, talk about the M5 brain. So M2 brain is a two-dimensional brain, as we saw that before, in a three-dimensional space. But M5 brain is a five-dimensional object. So this is like you know, a six-dimensional space, potentially depict a sheet. So we see here some perforations as sheets. So we see some kind of a features here that kind of shows that if we project that, let's talk about higher dimensions about M5. Now here, this is Calabi-Yau manifold. Again, I'm not showing the actual ones, which are there in Wikipedia. The things you can prove the actual three-dimensional thing, but it is a compactified aspect that shows how the Calabi-Yau manifold can come. So in theory, it involves a Calabi-Yau manifold. Shapes are compactified dimensions. They are complex six-dimensional shapes curled up at extremely small scale. So the curled up dimensions are one of the key aspects of the Calabi-Yau. Can imagine a complex twisted 3D shape, like a twisted flower or a multi-dimensional node to represent the compact effect. So that is one aspect. Now, physics diagram. Again, this is a black hole. Again, this is only a projection 2D, event horizon and light bending, and we see many effects of measurements, and we are seeing the actual simulations and actual measurements going on even now. So the visualization of the event horizon, black and the distorted space around is an abstract 2D plot, light paths bending due to the gravitational pull. In event as a red dash, so the event horizon is the red dashed circle, and light paths are bent. Gravitational lensing represent white curves. So these are the white curves, and the plot is highly abstract, gives an impression of light bending. So the black hole diagram represents event horizon. While it does not capture all the complexities of black hole physics, they provide a simplified conceptual view. Okay, so you got to gauge. Gauge theory is a very important thing, as we mentioned earlier as well. They show the invariance aspect, things like that. It brings out the invariant symmetry. So the gravity, and then how you interact with gravity. Again, that's the duality is the very high level. We're trying almost impossible things here. So connects theories of gravity and quantum field theory. The quantum gauge theory is represented as flat line. So here you have the gauge theory aspect, the flat line, simulating boundary of space where quantum field theory is. So quantum field theory is the one greatest thing achievement that heralded in the standard model, things like that, the key thing aspect with Feynman and other people getting to that. But it's a very weak theory is the one that is almost fully verified, I would say. The gravity theory bulk is represented as a Gaussian curve. So this is a Gaussian curve. That's a gravity theory of the bulk. Curved space, which is a dual to the boundary. So this is a dual to the boundary, and it's shown The arrow indicates the duality connection. So the duality connection is shown here. How is dual to that? Now, the duality diagram abstractly visualize a relationship, gauge theories, and gravity theories, and so that is the main idea. But it does not, of course, you cannot capture all the complexities. Provide a simplified conceptual view only right now. Okay, the next one is a level dimensional space time. Again, it is represented in the 2D aspect kind of thing on the plane of this one. So abstract representation. So again, 3D projections which may represent addition, Calabi or manifold. The spherical coordinates plots simply represent compactified space, extra dimensions like the Calabi or manifold. Simulate extra dimension, smaller sphere. So this smaller sphere is the one that extra dimensions. We'll have some dimension that compactified small scale. The visual output shows a larger sphere. This provides an abstract visual analogy of M-theory. So we briefly go through the aspect of the experimental challenges and future directions. So while M-theory is theoretically sound, there are no direct experimental observations. Cosmological observation of the cosmic microwave background gravitation could provide some indirect evidence of M-theory. Again, this analysis is going on, and we have new models that may help in that. Particle accelerators, large hadron collider, like I mentioned, may help in discover supersymmetric particles or evidence, which has not been done yet, but it's a new particle. So LHB collaboration and inflationary cosmology by Linden. All these will give some more insights into that. So key takeaways today's are, again, theory is a leading candidate, theory of everything, unifying fundamental forces of nature. It integrates quantum gravity, string theory, and cosmology, and that has potential to answer profound questions about the universe's origin and structure. That's where you want to find out. While direct experimental evidence is still lacking, M-theory's mathematical elegance and the predictive power make it a key area of research in theoretical physics. So Witten has gone into more detail about that, the physics. So conclusion, M-theory, ongoing episode. Theory offers a roadmap to the next frontier in understanding the universe, bridging gaps between quantum mechanics, general relativity, and cosmology. So research progresses, we may find new experimental avenues to test its prediction. Duff is going through that. So we'll open questions. And as I mentioned, this today there's not enough time. I have an appointment go now. But next week we'll go into the details. So I just want to give thumbs up on that. Questions provide insights, and then we'll have more Q&A discussions and so forth. The figures with the presentation obtained from the references as well as the standard lookup tables that's available for programming. Some of these are I program them and get the output for the plotting. Okay. So the references are Witten, and again the same kind of put together all the references briefly. Thank you very much, and I'll just give. This is a brief summary. I went through this, but I just put that. Probably during discussion we can go through some of it, and then upcoming YouTube M-theory. The question is, it's M-theory extendable to brain theory? That's what I am looking into, to even to include discontinuum physics, things like that. Will that help to unify physics? These are the questions we'll be asking. So episode 10 will continue analyzing emergent field with quantum matrix modeling, brain theory, general relativity to numerical relativity that Christopher briefly presented a few episodes. Thank you very much. And then if you have any particular comments, another few minutes, but then I had to go. But another few minutes I have.
Okay.
Thank you very much.
Thanks, Rajan. That was interesting. No, I don't have like too many comments or anything.
Okay.
I liked your use of or they matplotlib graphs or something.
Thank you.
Yeah, that was good. And wasn't entirely sure about like what functions did you use to represent the Calabi-Yau manifold, and why did you choose that one?
It's actually the program puts the I the program actually pulls in from the Calabi manifold important data. It just pulls data and then reploads in a 2D mention. So it's just a 2D thing. But we know Wikipedia, they have more detail, little bit more details, the graphics. But this is just a 2D representation.
Oh, that's great. Yeah. Okay, so you could have like multiple different copies of those then from different angles.
Exactly.
Well, that's very good. So okay, so that was really it in terms of the comments I have, because that was quite a brief presentation, I noticed.
Yes.
It was kind of over.
Yeah,
it was over before I realized. So I might have to go back and watch that again.
Yeah.
And then maybe I'll have more comments next. But next week, I might do a presentation then on the anamorphic perspective cosmology.
Great.
And that might be the final one on that. And then did you say that you have what episode number was this? Episode 9?
Yeah, so one more episode.
I thought this was episode 10 or 11 or something.
No, 9. This is 9. Then episode 10 is the last one. That will come in February.
This was going to be the last one, though.
Yeah.
Or you did say up to episode 10, but yeah, I also thought you said that M-brain theory would be the last one. Anyway, so what is the last one?
Emergent theories. So I have that. Probably I will show the next week. I have some slides already. I can show. I don't know how long. I can briefly show if you want, but next week we can. Yeah, okay.
Whichever.
So, like a couple of minutes.
Yeah.
Couple of minutes we can spend.
What do you think?
So the 10 episode. I know that. Can you see that?
Yes.
I will just leave the way it is. I'm not going to change.
So emergent theory. Yes. All right, numerical relativity. Well, emergent stuff. That's
emergent contemporary.
Yeah, like that a lot, don't you? So that can kind of cover a lot of different areas. What areas?
So numerical relativity, for example, and the computation model. I may edit this some of it, but I mostly
so numerical. Does that mean that it's in some different theories? Do you cover all of? Do you cover many of them, or why do you just focus on numerical relativity?
I thought that was the one that can explain the gravity aspect. For to incorporate that into the quantum mechanics. I think the way the general relativity is now, I don't think it can incorporate the quantum mechanics.
Well, that's what they say.
Ability, So
we already have technically that's already part of the what is it, the 120 cell model?
Oh yeah.
Although that's just like one explanation. Although I think it is. I mean, no, it's probably just. It could be one of like many explanations, but I don't know. I think it is pretty
discretizing space-time. So quantum mechanics talked about discrete. It's a discrete thing. So hopefully this will merge. They will come together in some manner.
Yeah, Penrose. He's always talking about, they always want to, what is it, quantize gravity or something like that.
Yeah.
And then he's saying, no, it would be better if they gravitize the quantum realm or something.
Yeah. Yeah, that's ongoing. Yeah, we'll discuss that after this.
Instead of discretizing gravity, you want to gravitize the quantum realm because there's some problem with quantum or quantum mechanics because of the uncertainty. But I think that's kind of interesting enough. Like I didn't really pay too much attention to Penrose's opinions on that. But if you look at the 120 cell theory of everything model. That's exactly what that does. It creates space-time warpages in like discrete lattices of the quantum mechanics. So it's gravitizing the quantum mechanical realm rather than attempting to quantize gravity and break it up into little lumps. So I think that's another reason why potentially the 120 cell is the correct answer.
Oh, okay. So after this, our thing comes in. So anyway, we'll go into detail after.
Oh,
but again, neutron merger stars.
Interesting.
Algorithms, like I mentioned, so
great.
And these people have that numerical methods. Gravitational wave astronomy, numerical. So that helps to figure out about the gravitational waves a little more.
Oh, absolutely. Yeah.
So LIGO and Bertie, all these people are.
That's very interesting.
Binary neutron star mergers, black hole formation. These people are discussing that.
Oh, great.
Okay, I think they mainly. I don't think I may look over challenges and then see whether anything I need to add. Probably I'll leave
a few images maybe. This is quite evocative stuff, but maybe not. It's up to you.
Yeah, so I have some space here. I put to then I say we're going to movie, things like that. So that's basically. I mean, right now that he said, I don't know whether I will ever change anything, but we'll see. I mean,
anyway,
if you have some ideas,
I like
because the last episode. Yeah, let me know. Yeah.
Okay. See you next week then.
Okay. So, anything about your leave and things like that? Did you get a chance?
Yeah. Yeah, I looked into that.